So we can apply free body diagrams to understanding what's happening. So these are some rocks that Davy Hutchinson threw, all right, and they're moving through the air. They're going to hit something. We're not going to talk about what, but he's throwing a rock. So initially that rock is in his hand, and we have gravity pulling it down, and his hand is applying normal force to it. So gravity, which we call force grav, sometimes it's just force G, and we have force norm, which is normal force. These two arrows are the same magnitude. They're parallel and they're opposites. They cancel each other out, so that rock hasn't started moving yet because Davy Hutchinson has not thrown it towards his intended target. Now, we can see that there is no net force here, so we're not really worried about anything else. We just know it's not accelerating. Now, eventually, Davy is going to throw that rock. He is going to apply some force to it in the direction that he wants to throw it, and we call that force applied. It's still going to be under the force of gravity. Okay, he might, if he gets it fast enough, there might be a little bit of force of air resistance. Okay, but that force normal is going to be gone after he throws it. So we can see that the force of gravity is not balanced out, so the rock is going to start falling, but it's also going to start throwing. For Davy's sake, we hope it makes it. For Miss Hutchinson's sake, we hope that it doesn't, but these forces are acting on it. We can see these forces are unbalanced, and so it's going to accelerate. Now, if we want to know how much it's going to accelerate, we can look at the forces that he's applied to it. And we're going to need newtons to figure that out, but that's what's useful about it. So let's say that we know that the force of gravity is 9.8 newtons, which is a pretty common amount of that to see. And let's say that we know that the force applied is 10 newtons. And we know that the force of air resistance is going to be about 1 newton in this case. Now, these numbers are just made up, but there are ways to actually get those numbers. So we can calculate the acceleration in two different directions. One, we already know the downward force is 9.8. We already know that's what it is because it's not opposed by anything else, and it's not affected by these two forces because they're perpendicular. Okay? But the 10 and the 1 do affect each other. Now you could draw the arrows out, but 10 is getting a little further than I want to draw. So I'm just going to say that I've got 10 newtons, and that's going to be in the positive direction. And the 1 newton is in the opposite direction, so that's going to be negative. That's 1 newton. And I'm going to add those together to find the net force. Okay? And that net force is going to be 9 newtons, and it's going to be positive. So we know that that's 9 newtons. And we say that's equal to force. Okay? Now, if you ever see that F and F equals ma, it's talking about net force. It's got 9 newtons of force to the right. So let's just talk about right and left for now. We can come to the other one in a minute. But why it's important to know the acceleration down of this rock is now that we know it's 9 newtons, we can use the equation F equals ma, which is the mathematic version of Newton's second law. Okay? So force is equal to 9 newtons. So we can plug in those 9 newtons for that. Now we still need a couple more pieces of information, but we had a lot of steps to understand how to find the force using that free body diagram. So let's say that the rock has a mass of 1 kilogram. Okay? I can plug that in for the mass, and I've got 9 newtons. And I know it's 9 newtons applied to a 1 kilogram rock, which is a pretty good sized rock. Not going to be very fun if it hits anybody. But I can solve for the acceleration. Okay? So I don't need you to do this yet, but I'm just showing you why we have the free body diagram in the first place. So I will divide both sides by 1 kilogram. 9 divided by 1 is 9. Newtons divided by kilograms is meters per second squared, or meters per second. And that's going to be the acceleration of that rock as long as Davy Hutchinson is putting 9 newtons of force on it. So every second that he is throwing it, applying that much force, it's going to get 9 meters per second faster. So if it's in his hand being thrown for 2 seconds, it's going to be going 18 meters per second, and it is going to go through the air. Now it's also accelerating downward. We're not going to solve that for now. I really just wanted to show you why you would want to know the net force of something, because now we can solve for its acceleration.